Welcome to Electronic Geek. In this video we will be starting with universal gates. So what are universal gates? Universal gates are the gates that by using which we can make any gate. So there are two gates which are called as universal gates, that are NAND and NOR. So by using NAND and NOR we can design any gate. Let's start with NAND gate as a NOT gate. So in order to use NAND gate as NOT gate and other gates too, there are two laws which are very useful, and that are the basic laws for simplifying any Boolean expression. Okay, so these laws are called as the De Morgan's law. So I have written these two De Morgan's law in the top right corner, so it is easy for us to design the circuit. So first law says a plus b the whole complement is equal to a complement dot b complement, and the other law is a dot b the whole complement is a complement plus b complement. So these two laws are called as the De Morgan's law, and using these laws we will be using NAND gates to make other gates. So first of all, let's start with the NOT gate. So click on P, and IC number of NAND gate is 7400. So search for 7400, and we will be using this 74HC00. HC is for high speed CMOS. Then again the next component is logic toggle. Search for it, and to check our output we'll be using an LED, red color LED. So now we have all the components with us, and let's start by making NOT gate using NAND gates. Okay, so if you see the case of a NOT gate, the truth table of NOT gate, at a time in case we have only a single input and the output is in the inverted form, like you have an input called A, the output is A bar. So we select this NAND gate, place it here in the schematic, zoom a bit. Yeah, if we see here, this is a two input NAND gate, and the NOT gate that we want is a single input. So what could be done is we can short these two terminals and give it to a common let's say common pin. So we will select toggle switch over here, place it, connect it like this. The two inputs are now shorted, and the output of NAND gate, the logic expression of output for NAND gate is A dot B bar. So in this case, as the input is common, it will be simply A bar. So select this LED and place it at the output, rotate anti-clock, select move. Go to terminals, select ground and place it. See, now this particular circuit is equivalent to a single NOT gate. Let's run the simulation. See, when the input is low, output is high, and when the input is high, output is low. So this is how you can make a NOT gate using a simple NAND gate. Let's stop that. Now the next gate that we will do is AND gate using NAND gates. So in if you see it, the output of AND gate is exact the inverted for output of the NAND gate. So what we need to do is we will be taking the output of a NAND gate and we will be giving it to an inverter circuit. But again we have a constraint, we cannot use a NOT gate. So we will be modifying this circuit a little bit. Okay, we will remove this wire, delete wire, and we go here in the component mode, we select other toggle switch and we will be connecting it. Remove LED for the time being. Now this particular output will be given to an inverter gate. Few minutes back we saw how to make an inverter gate. What we will do is we will be shorting these two input pins and we will be connecting straight to the output like this. And now place the LED. We'll see what results we get. Terminals, ground. Yeah, so firstly we'll be seeing the truth table of an AND gate. The output is high only and only if both the inputs are high. So here is the truth table of AND gate. You can see the output is high only and only when both the inputs are high. Rest all the cases we get the output is low. So let's start. See, right now it's 1 0. So AND operation of 1 and 0 gives you 0. It's 0 0 still 0 1. Let's try for 1 1. The output is high. So this particular circuit is equivalent to a 2 input AND gate. Now the next circuit we will be doing is how to make an OR gate using NAND gate. So we'll stop the simulation. And for OR gate what we need is A plus B at the output, and by using NAND gates what we get is A dot B bar. So how we can use this to make an OR gate? If you see here this boolean identity, the second one, A dot B the whole bar is equal to A bar plus B bar. We will use the same thing to make an OR gate. So let's start. We'll delete this entire circuit, go to components mode and select the NOT gate. Now we can achieve this by taking the individual outputs like this. We will be giving these two particular pins will be shorted and will be given to a particular input, let's say A, by which we will be getting A bar, and which later on inverting again will be giving us A. So that this is our shorted connected to a logic toggle. Now we will be using this same kind of circuit below. Short the 2 pins. Use a logic switch. Now if this particular input is A, the output that we are having is A bar, and if this is B, we are having B bar. What we need is A plus B. Now if we give this particular input and this particular output to another AND gate, let's see what we get. Select this, place it, output goes to this input and output goes to this input. Now what inputs are fed to this NAND gate are A bar and B bar. So what will happen is it will be A bar dot B bar the whole bar, and if you apply the second De Morgan's theorem over here, what you will be getting is A bar complement plus B bar complement, which is equal to A plus B. Okay, let's see it. Go to component and place an LED. So what's happening in this case is you are complementing the output twice. Okay, so let's start the simulation. So yeah, right now both are 0. So as per OR gate, 0 plus 0 gives 0. Now 0 plus 1. See, LED is high. Now we'll lower this down and see, it's again high, and 1 and 1 also gives 1. So this is how you can make an OR gate using a NAND gate. Now the next gate we will be doing is NOR gate. How can you make a NOR gate using a NAND gate? Okay, so if you see this particular circuit clearly, we are at least getting the OR gate output, what we need to do is we need to invert this once again. So what we will be doing is this particular output will act as an input for the next NAND gate, and we can get the output. Please the LED. Let's start our simulation. See, 1 plus 1 in case of OR gives 1. See, this is, we are getting the LED as low, so this is our NOR gate. We'll try the other simulations too. See, it is still low. 0 plus 1 is 1 and it's getting inverted, so 0. And see, in case of 0 0, this sum is 0 and we are getting the inverted output as 1. So this is how you can make a NOR gate using NAND gate. Now comes the last one, which is the XOR gate. XOR gate is a bit complicated because of its logical equation. So logical equation of XOR gate is A B bar plus B A bar. So what you need is, we need inverted outputs, individual inverted outputs, plus we need to have some kind of an OR operation also at the end. So let's see how we can make it. Now let's clear this particular thing, and we'll be seeing the XOR gate truth table. See, XOR gate can be also said as, when odd number of inputs are high, the output is high. See, this both the inputs are low, here both the inputs are high, but here either is high, so we are getting the output as high. So let's start with designing of an XOR gate. So as discussed earlier, what we need is an individual inverted outputs. So first thing that we will be doing is, we'll be needing A bar and B bar, so like this, and we will be shorting these two pins to get A bar, and same we'll short this to get B bar. Yeah, so now we are having the output as A bar, and here we are having as B bar. So we will be using another NAND gate over here. So this will be going over here. Now if we see our terms, it is A B bar plus B A bar. So what needs to be done is, with this A, we need to take B also over here. Okay, so we can do like this, route the connection. Now what we are here having is, A bar is the first input and B is the second. So NAND operation of A bar and B gives A bar B the whole bar, which is equal to A B bar. So what you are having on the output is A B bar. And similarly, if you do the same thing over here, let's keep it like this. So now what we are having on both the output are, on one output of NAND gate we are having A B bar, and on the other we are having B A bar. Now what needs to be done is, we need the OR. Okay, so we need the OR operation. So again we will be using this boolean the De Morgan identity for getting this. So connect this outputs to the input, same with this, and for checking we will be using this LED. So this is our circuit for an XOR gate. Let's test it. Start simulation. Right now it is 0 0, LED is off. Let's change this to 0 1, LED is on. To 0 1, see the LED is on, and to 1 0, the LED is off. Thus we verified the results for NOT gate, AND gate, OR gate, NOR gate, and for XOR gate. So in this way we can use NAND gate as a universal gate to derive the other gates by using these De Morgan's law, which are a plus b the whole bar is a bar dot b bar, and the other one is a dot b the whole bar is a bar plus b bar. So in this way NAND gate can be used as a universal gate. In the next lecture, we will be seeing how NOR gate can be used as an universal gate. So this is it for this video. Thank you for being till here. Thank you so much. Do like, share, comment, and subscribe to my channel. And thank you for being till here. Thank you so much.